Hello there and welcome back to this video series on control systems. Before we go into the present video, we'll do a quick review of what we have seen already. We have seen that it is possible to simplify a complex block diagram into one single rectangular block. This can be achieved either by writing the equations and eliminating unwanted variables, or by block diagram reduction techniques, or by signal flow graphs and Mason's gain formula. The signal flow graph and block diagram reduction we'll see later. After watching this video, you'll be able to specify the purpose of Laplace transform and perhaps find the Laplace transforms of a few simple functions. To begin this video, we'll try to see why we need Laplace transform in this context. Dynamic systems are generally represented by differential equations, and linear time invariant systems, we'll see what they are later, and they are represented by linear differential equations with constant coefficients. Solving such equations at times may prove to be cumbersome, a little bit tedious, a little bit roundabout, and thus we use Laplace transforms to convert the differential equation into algebraic equation, and then simplify and then take inverse transform to find the solution. We will see the sequence of steps involved in solving a problem related to a solution. We have a system, and then for that system, starting from physical principles, we'll derive the differential equations, and then we take the Laplace transform of the differential equation, which Laplace transform converts the differential equation into an algebraic equation, and then we simplify, and once we simplify the final result, we take inverse Laplace transform and we have the solution. Okay, incorporating initial conditions almost is seamless with Laplace transform. Okay, and in subsequent slides we'll see how Laplace transform converts a differential equation into algebraic equation, and how the concept of Laplace transform gives rise to transfer function, specifically when we say transfer function with zero initial conditions. With that, we'll try to see the definition of Laplace transform. If f of t, where t is the time, that is why we call this f of t is in time domain. If f of t is the function and you need to take Laplace transform of this function f of t, you'll do two things. One, you multiply it with e power minus st, and two, you'll integrate with respect to time with 0 to infinity. Okay, so 0 to infinity e power minus st f of t is the Laplace transform of f of t. This pound-like symbol is used to indicate Laplace transform. Once you do this, the result will be in terms of the variable s, and so we say this f of s is the Laplace transform of f of t. So this f of t is the function whose Laplace transform is sought. You multiply it with e power minus st, then integrate between 0 to infinity with respect to t, you get the Laplace transform of f of t. Typically, you use lowercase letter to indicate time domain functions, and the uppercase letters, okay, to indicate the Laplace transform domain. Lowercase f is time domain function, uppercase f is the Laplace domain function. So this is Laplace variable, this is time. Okay, Laplace transform exists only if the integral converges, and the region over which it converges is called region of convergence. Let us try to find the Laplace transform of such simple function shown over here. F of t is 1 if t is greater than or equal to 0. You can see all towards the right hand side it is 1, all towards the left hand side it is 0. That is, when we integrate between the limits 0 and infinity, that covers all the portion towards the right hand side of the y-axis, that is ft axis, from 0 all the way up to infinity. The value of the function is 1. With that idea, we will try to simplify this. Integral 0 to infinity e power minus st into f of t. F of t is 1 within the limit 0 and infinity. So you put 1 here and then try to simplify. You try to simplify. E power minus st integral is e power minus st by minus. Between the limit 0 and infinity, it is 1 over s. The function f of t is called a unit step function, and it is represented by u with subscript s. U subscript s of t. With that, we conclude this video and summarize. We say that Laplace transform enables us, 1, to solve linear time invariant differential equations and to define transfer function. We'll see what transfer function is later. And then we saw that to take Laplace transform of the function f of t, t being the time, we first multiply it by e power minus st, then integrate between limits 0 and infinity with respect to the variable t. When you complete this integral, you get an expression in s that we call Laplace transform of the function, represented by the symbol Laplace transform L or cursive L of f of t. Typically, you use lowercase letters to indicate time domain functions and corresponding uppercase letters to indicate Laplace transform of it. Okay, and then we have seen that Laplace transform of unit step function is 1 over s. I think that's all we have for now. Have a great day.